Right now, your computer is running dozens of programs. A browser, a music player, maybe a compiler, a chat app. But here's the thing, a single CPU core can only execute one process at a time. So every few milliseconds, the Linux kernel faces a critical question. Which process gets the CPU next? This decision happens thousands of times per second. Get it wrong, and your music stutters while a background task hogs the processor. Get it right, and everything feels seamless, as if each program has the CPU all to itself. The algorithm behind this decision is called the Completely Fair Scheduler, or CFS. It's been the default scheduler in the Linux kernel for over 15 years, powering everything from Android phones to cloud servers. And its core idea is surprisingly elegant. Instead of complex rules about who deserves what, CFS follows one simple principle: always run the process that's been treated most unfairly. Let's see how it works. The fundamental problem is straightforward. You have multiple processes that want to run, but only a limited number of CPU cores to run them on. The scheduler must decide who runs next and for how long. Your first instinct might be round robin, just take turns. Each process gets an equal time slice, then yields to the next. Simple, but processes aren't all the same. Some are interactive, like your text editor, which mostly sleeps waiting for keystrokes. When you do press a key, it needs the CPU immediately, but only for a tiny moment. Others are CPU-bound, like a video encoder or a compilation job that wants to crunch numbers for hours straight. A good scheduler must balance three competing goals. First, fairness. Every process deserves its proportional share of CPU time. Second, responsiveness. Interactive programs must react quickly, not lag behind batch jobs. And third, no starvation, no process should wait forever while others monopolize the CPU. Balancing all three is the real challenge. Before CFS, Linux used the O1 scheduler, introduced in kernel 2.6. It was built around two arrays of priority queues, called the active array and the expired array. Each array had 140 priority levels. Every process sat in the queue matching its priority. To find the next process to run, the scheduler checked a bitmap to find the highest priority non-empty queue. That lookup was constant time, hence O1. Each priority level had a fixed time slice. High-priority processes got longer slices. Low-priority ones got shorter slices. When a process used up its slice, it moved from the active array to the expired array. When the active array was completely empty, the scheduler simply swapped the two arrays. Clever design, but it had real problems. The fixed time slices created unfairness under heavy load, and detecting whether a process was interactive relied on fragile heuristics that broke in edge cases. Ingo Molnar, the kernel's scheduler maintainer, decided it was time for something fundamentally different: a scheduler built on math, not heuristics. CFS threw away priority arrays and interactivity heuristics entirely. In their place, it introduced one elegant concept: virtual runtime or vruntime. Every process in the system has a vruntime value. This counter tracks how much CPU time the process has received, but not raw wall clock time. It's weighted time, adjusted by the process's priority. When the scheduler needs to pick the next process, it follows one simple rule: pick the process with the lowest runtime. That's the process that has received the least CPU time relative to its fair share. When a process runs on the CPU, its runtime increases. When a process sleeps, waiting for input, waiting for a network packet, its runtime stays frozen. This creates a beautiful natural behavior. Interactive programs that sleep frequently accumulate very low runtime. When they wake up, they naturally jump to the front of the line because their runtime is the lowest. No special interactivity detection needed. No heuristics. Responsiveness emerges automatically from tracking fairness. The formula is straightforward. Runtime increases by the execution time multiplied by the ratio of the default wait to the process's wait. CFS needs to quickly find the process with the lowest runtime. It also needs to efficiently insert and remove processes as they wake up, fall asleep, or finish their time slices. The data structure that makes this possible is a red-black tree, a self-balancing binary search tree. In this tree, each node represents a runnable process. The key used for sorting is the process's runtime. Since it's a binary search tree, the leftmost node always holds the smallest runtime, and that's the next process to run. Finding the leftmost node takes O of log n time. Inserting a new process when it wakes up is also O of log, and removing the selected process when it starts running is O of log n. The tree rebalances itself automatically through rotations, maintaining its balanced structure. This means even with thousands of runnable processes, the scheduler makes its decision in logarithmic time. And the kernel caches a pointer to the leftmost node. So in practice, selecting the next process is actually O of 1, a single pointer dereference. The tree ensures that pointer always points to the fairest choice. Unlike the O1 scheduler with its fixed time slices, CFS calculates each process's time slice dynamically, based on how many processes are competing for the CPU. CFS defines a scheduling period, the target time window within which every runnable process should get at least one turn on the CPU. By default, this period is about 6 milliseconds when there are few processes. Each process gets a fraction of this period proportional to its weight. If 3 equal weight processes are runnable, each gets 2 milliseconds. If 8 are runnable, each gets about 0.75 milliseconds. This means when the system is lightly loaded, processes get longer time slices and fewer context switches, great for throughput. When it's heavily loaded, slices shrink to keep latency low and responsiveness high. But there's a floor. CFS enforces a minimum granularity of about 0.75 milliseconds per time slice. Below that, the overhead of context switching would waste more CPU time than it saves. The formula is simple. A process's time slice equals its weight divided by the total weight of all runnable processes, multiplied by the scheduling period. Dynamic, proportional, and adaptive. Not all processes deserve equal CPU time. A background log rotator shouldn't compete equally with your interactive IDE. Linux uses nice values to express this, ranging from -20 for highest priority to +19 for lowest priority. The default is 0. You can set a process's nice value with the nice or renice commands. But CFS doesn't use nice values directly. Instead, it maps each nice value to a weight using a carefully designed lookup table. Nice 0 maps to a weight of 1024. The table is designed so that each step in nice value changes the CPU share by roughly 10%. Nice -1 gets about 10% more CPU than nice 0. Nice +1 gets about 10% less. Here's where it connects to runtime. When a process runs, its runtime increases by the execution time multiplied by the default weight divided by the process's own weight. A high-priority process with a large weight sees its runtime increase slowly. A low-priority process with a small weight sees its runtime climb quickly. Since CFS always picks the lowest runtime, the high-priority process naturally gets more CPU time. No heuristics, just math. What happens when a sleeping process suddenly wakes up? This is where CFS shows its elegance. Imagine a text editor that's been blocked waiting for your keystroke. While it slept, its runtime stayed frozen. Meanwhile, the CPU-bound compiler that was running kept accumulating runtime. Now you press a key. The editor wakes up. CFS immediately compares the editor's runtime to the currently running process's runtime. If the waking process's runtime is sufficiently lower, specifically, lower by at least the minimum granularity, CFS preempts the running process. The compiler gets pushed back into the red-black tree, and the editor takes over the CPU. This is why interactive applications feel so responsive under CFS. They sleep frequently while waiting for user input, which keeps their runtime low. When they finally need the CPU, they jump right to the front. But CFS also prevents gaming. If a process deliberately sleeps to manipulate its runtime, CFS adjusts the waking process's runtime to be no lower than the current minimum runtime in the tree. This prevents a single process from starving everyone else by gaming the sleep mechanism. Let's put it all together with a concrete scenario. You're editing code in Vim while GCC compiles a large project in the background. Both processes start with a runtime of 0. GCC immediately starts crunching code, and its runtime climbs rapidly. Vim sits idle, waiting for your keystrokes. Its runtime is frozen at 0. You press a key. Vim wakes up. Its runtime is far below GCC's. CFS instantly preempts GCC and hands the CPU to Vim. Vim processes your keystroke in a fraction of a millisecond, then goes back to sleep. GCC resumes right where it left off. This pattern repeats throughout your editing session. Every time you type, Vim gets the CPU immediately because its runtime is always the lowest. Yet GCC still receives the vast majority of total CPU time because Vim barely uses any. Both processes are happy. Vim feels perfectly responsive. GCC gets nearly 100% of the CPU between your keystrokes. No priority tuning was needed. No interactivity flags. The runtime mechanism handles everything automatically. Fairness and responsiveness emerge naturally from one simple rule: always run the process that's been treated most unfairly. The completely fair scheduler changed Linux scheduling by replacing complexity with elegance. Let's recap what makes it special. 1. Instead of heuristics and priority arrays, CFS tracks virtual runtime, always running the process that's received the least CPU time. 2. A red-black tree keeps this lookup efficient at O of log n, with the leftmost node cached for instant access. 3. Time slices are dynamic, adapting to system load. More processes means shorter slices to maintain responsiveness. 4. Nice values map to weights that naturally adjust how fast runtime grows, giving higher priority processes more CPU time through pure math. And 5. Preemption happens automatically when sleeping processes wake up with low runtime, making interactive applications feel responsive without any special heuristics. CFS has been the default Linux scheduler since Kernel 2.6.23, released in 2007. It runs on everything: Android phones, Raspberry Pis, cloud servers, and the world's fastest supercomputers. Its design is a reminder that sometimes the best solution isn't the most complex one. It's the one that finds the right abstraction. Thanks for watching, and I'll see you in the next one.